Good morning. Now, this is class 2 of our module 1. The topic is equation of an ideal gas. Hope you all know the equation of ideal gas, which is equal to PV equal to nRT. Okay, so today we will learn how we obtain this equation from various fundamental gas laws. Okay, now this is about the ideal gas equation. Boyle's law. All these laws I think you have learned in your lower classes. What is Boyle's law? The pressure of a fixed mass of gas held at constant temperature is inversely proportional to its volume. That is PV equal to constant. Now what is Charles' law? Volume of a fixed mass of gas held at constant pressure is directly proportional to its Kelvin temperature. That is V by T is equal to constant. Now Gay-Lussac's law, that is the pressure of a fixed mass of gas held at a constant volume is directly proportional to its Kelvin temperature, that is P by T equal to constant. So in all these three laws, all the sentences are same except a few variables are changing. That is, in the first case, you can see that Boyle's law is about constant temperature, whereas Charles' law is at constant pressure. All the sentences are the same. Then what about Gay-Lussac's law? It is about constant volume. Okay, now combining all these laws, that is Boyle's law, Charles' law and Gay-Lussac's law, we can write that if P, V and T are all allowed to vary, these three laws become PV by T equal to constant. Now the value of the constant depends on how much gas there is. That is, it is proportional to how many moles of gas there are. So including that also in the above equation we can write PV by T is equal to Rn or PV equal to nRT, which is nothing but our ideal gas equation. Here N is the number of moles, R is the constant of proportionality, which can also be called by the name universal gas constant, and that is found to be the same for almost all gases. Now any gas that obeys this ideal gas equation, that is PV equal to nRT, is called ideal gas, and the equation is called ideal gas equation or equation of state for an ideal gas. So in such case we call the capital letter V in equation 1 as total volume of gas. N is called number of moles and R is the universal gas constant, as I said before. So the equation can be written as PV equal to RT, that is PV equal to nRT can also be written as PV equal to RT considering N, that is number of moles, equal to 1. So in this case V will be called as molar volume. Okay, that is our equation 2, PV equal to RT. Now see, equation 1 can also be written as P equal to N Na by V into RT by Na. Okay, what is your first equation? PV equal to nRT. So here we are rewriting that equation 1. It is written like this. P equal to Na by V into RT by Na. See, Na and Na are the same. So if we cut this Na and Na, this will be gone. So what is left behind? PV equal to nRT. So that is the equation 1, PV equal to nRT. So what we are doing is we are just multiplying and dividing with a constant Na, which is nothing but the Avogadro number. Okay. And what is Avogadro number? 6.023 into 10 raised to 23 molecules per mole. Now the first term on the right hand side, that is the first term on the right hand side, means this one. This is the right hand side. So the first term, this one on the right hand side, is nothing but the number of molecules per unit volume, and it can be written as small letter n. Okay, now in the second term, which is your second term, this one RT by Na, or we can just write, just exclude this T, R by Na. That is nothing but Boltzmann constant, whose value is given by this. Okay, hence the equation of state for an ideal gas can also be written as P is equal to this. We already said it is equal to N, and this one R by N is the Boltzmann constant. Okay, what is Boltzmann constant? K, and finally this particular T. So this particular equation or the ideal gas equation or equation of state for an ideal gas can also be written in another form. What is it? PV equal to nRT or P equal to nKT. This is obtained from this equation. That is, P is written as such. Instead of n Na by V, as we already said, it is equal to n. So this is replaced by small letter n. Then R by Na is Boltzmann constant. R by Na. So that is K, and T is written as such. So P equal to nKT, which is written here. So PV equal to nRT. The another form is P equal to nKT. Now, next is we are dividing both sides of equation 2 by molar mass. Another representation for the ideal gas equation. For that, you have to divide equation 2. What is equation 2? PV equal to RT. You are dividing that equation 2 by molar mass mu. So, what will be that? PV by mu equal to RT by mu. Okay, so see, this is written here. PV by mu equal to RT by mu. From that you have to find P. So you will get this equation. And from that P equal to RT is kept as such. Then instead of mu by V is written as rho. See here rho. That is written here. And this under the denominator you have got a mu, that is written as such. So this is another form of ideal gas equation. That is P equal to RT rho by mu, where rho equal to mu by V. So equation 1, 2, 3 and 4 are all equivalent forms of equation of state for an ideal gas. Okay, various forms. Now we will learn about real gas. What is the definition for real gas? A gas that does not obey ideal gas equation, right? Okay. Now ideal gas equation is followed quite well provided that temperature is well above the temperature at which it can be liquefied merely by compressing it. This temperature is called critical temperature. So here you got a definition for critical temperature. What is critical temperature? Critical temperature is a temperature at which a gas can be liquefied just by compressing it. Okay, so at temperatures above this critical temperature, ideal gas equation is well obeyed. That is, ideal gas equation is obeyed at all temperatures which are above critical temperature. What is critical temperature? It is a temperature at which a gas can be liquefied just by compressing it. Okay, we know that real gas actually deviates from ideal gas behavior. Okay, now if you want to understand how much the real gas deviates from ideal gas behavior, the only thing that you can do is you just take the ratio PV by RT. Okay, and if this PV by RT is close to 1, then this real gas obeys ideal gas behavior. If it is far away from 1, then it actually deviates from ideal gas behavior. Now this ratio PV by RT is called compression factor. Okay, so this is one way by which you can decide whether a given real gas obeys ideal gas behavior. That is, you just take the ratio of PV by RT, that is called compression ratio. It is denoted by the letter capital letter Z. If it is close to 1, then the given real gas obeys ideal gas behavior. If it is far away from 1, then the real gas does not obey ideal gas behavior. Okay, now let us see its interpretation related to pressure. That is, for most real gases at very high pressure, it is found that this Z, the ratio PV by RT or Z, is greater than 1. Okay, now as the pressure is lowered, Z becomes again lowered, and then it increases a little bit, but it will reaches a value less than 1. Okay, so at lower pressures, Z will rise again. So for all gases, as pressure approaches 0, PV by T approaches R exactly. So R is called by the name universal gas constant or ideal gas constant. Okay. Now in the limit of very low pressure and high temperature, all gases behave very closely to the behavior of ideal gas. That is, at what condition? all gases behave like an ideal gas. What is the condition? At low pressure and high temperature. This is very important. This condition, at low pressure and high temperature, almost all the gases are almost all gases behave like ideal gas. Now this is another way. So now we have studied about one of the ways of determining whether how a real gas behave closely to that of an ideal gas. Okay, now that is by finding the ratio PV by RT, or compression ratio. You take the ratio and see whether it is close to 1. If it is close to 1, then the real gas behaves like an ideal gas. If it is far away from 1, then it does not obey the ideal gas behavior. Now another way to decide whether a real gas obeys ideal gas behavior is to draw isotherms. Okay, what are isotherms? They are nothing but pressure versus volume plot that are drawn at constant temperatures. Okay, here you can see various isotherms. Pressure is plotted along y-axis and volume V is plotted along x-axis, and these plots or the various lines that you can see over here are all isotherms, and they are plotted for different temperatures. Okay, and for an ideal gas, these isotherms PV equal to constant are in the form of rectangular hyperbolas. So they are for real gases at high temperatures. Now at low temperature, departure from ideal gas equation occurs. Okay, so I already said a real gas behave like an ideal gas at which condition? At a low pressure and high temperature. So at a high pressure and low temperature, what happens? Definitely there will be deviation or departure from the ideal gas equation. Okay. Now consider the behavior of a gas at a given temperature, starting from right hand end of each isotherm and then gradually moves to the left. Okay, that is, you are starting from, all these are isotherms. All these are isotherms in various shapes. They are plotted at different temperatures. Now we are beginning our study from the right hand end, that is from here, from this side, right hand end, to the left hand end. Okay, all this the hottest isotherm has the shape of a hyperbola. That is the first one that is given. Now at slightly lower temperature, a kink develops in the isotherm, and at the critical temperature, the kink develops a local horizontal inflection point. The isotherm for critical temperature is the critical isotherm. It is marked as Ci on the sketch. Okay. The meaning is that at slow temperature, and that is at lower temperature, that is somewhere over here, you can see a kink. This portion, a kink can be seen, and that is seen only at low temperature. Okay, and at critical temperature, what happens? The kink that is shown will develop into a horizontal inflection point. This one. Okay, now Ca is nothing but the critical isotherm. So just draw the figure and explain the various parts. That is enough. Okay. Now for temperatures below critical temperature, we refer the gas as a vapor. That is in the vapor state. Here you can see the vapor state. Okay, vapor exists only at temperatures below critical temperature. Then as you decrease the volume, what happens? Pressure increases until you reach the dashed curve. You can see a dotted line over there, right? And at this point, some of the vapor liquefies. See, you can see both liquid and vapor phase coexist, right? Okay, you are just explaining the figure, that is it. Now as the volume is decreased continuously, what happens? More and more vapor liquefies. More and more vapor liquefies. That is this one. Here you can see vapor plus liquid coexist, and after that most of the vapor liquefies and you can see only liquid, and that is shown by this vertical line. Only the liquid phase exists. In that region liquid and vapor are in equilibrium, and after that almost all the vapor liquefies. So near the right hand end of the horizontal portion there is just a small amount of liquid, and at the extreme left, which is shown by that vertical line, most of the substance is in the liquid phase. After it is all liquid, and further increase of pressure will decrease the volume only to a very small extent. Why? Most of the liquid is compressible. Now that isotherm is almost vertical, so the isotherm that represents the liquid phase is completely vertical. See the vertical line, this is the liquid phase. Now some definitions. The temperature of critical isotherm is critical temperature. Pressure and molar volume at horizontal inflection point of the critical isotherm are called critical pressure and critical molar volume. Now the horizontal inflection point is the critical point. So what is critical temperature, critical pressure, critical molar volume and critical point? All these definitions comes in this paragraph. So here our aim is to understand first of all there is a derivation of ideal gas equation. Then we learn about 2 points. Which are the 2 points? How you can see or how you can say that a real gas behave closely to that of a ideal gas. One method is to find the compression factor PV by RT and see whether it is close to 1 or greater than 1. That is one way, and the other way is to interpret from the isotherms. And so just draw this graph and explain the various parts and all each of these terms and all. Okay, so that is enough for today. This is all about equation of an ideal gas and the various ways of determining how closely a real gas behave like a ideal gas, or what are the ways of determining whether a ideal real gas behave similar to that of a ideal gas. Okay, that's all for today. Thank you.